Gibson here. Today we're going to continue looking at the concept of acceleration, but for a special case, a free-falling object in the presence of Earth's gravitational field. And then as we do that, we're also going to introduce two equations that we can use to analyze the motion of objects that have velocity and are accelerating. So our first objective is to describe the motion of an object in free fall. The second is determine the velocity and the displacement at any time after an object is dropped from rest. So basically ask the questions, how fast and how far has the object traveled if we drop it in the presence of Earth's gravity? So let's do a little review here. We've already introduced the concept of acceleration, but let's remind ourselves it's the rate at which the velocity of an object changes. So another way to describe that is the change in velocity over the change in time. Now, change in velocity can either be the magnitude or speed or also its direction. So if either one of those is changing, we have acceleration. So the car here could be speeding up or slowing down, but it could also be changing directions. All of those would be a form of acceleration. The symbol for acceleration is a small a, and the default units of measure are meters per second squared. And mathematically, how we can solve or calculate the acceleration is to divide the change in velocity by the change in time. And the other notation that we've used before is to find the change as the final velocity minus the initial velocity, and the final time minus the initial time. All right, let's watch a little video that'll get us thinking about free fall, and then we'll do some analysis of that free fall. All right, so that movie was made a little while ago, so I'm sure they found even taller structures to bungee jump off of, but 720 feet and 8 seconds of free fall, that would be quite a ride. Okay, so the first thing we're going to define here is when we are falling in the presence of gravity, what rate of acceleration do we experience? And that rate is unique to the Earth's surface, and it is 9.8 meters per second squared. Now it's close enough to 10, so for the problems that we're going to work on, we can simply use the value of 10 meters per second squared. Now, the acceleration of a body in free fall does not depend on the mass of that object. I think in class last week, we dropped a wad of paper and a calculator and found that they both hit the ground at the same time, even though they have very different masses. And that holds true as long as we can ignore wind resistance or it's negligible. Now, if we go to a different heavenly body rather than Earth, such as our moon, we would see that the acceleration is much smaller because the moon itself has less mass than the Earth. It's about 1/6 of the Earth, so it would be around, let's see, 1/6 of 10 is about 1.6, 1.7 meters per second squared. So if you've seen the pictures of the astronauts jumping around on the moon, you can see they, with just a slight little jump, they can go quite high in the air. That's due to the lower acceleration due to gravity. All right, so we got our bungee jumper ready to go here. So let's release him, let him fall. And we're going to take a snapshot of his position here every 2 seconds, okay? And the first question we want to ask is, how fast is the bungee jumper falling? So we have this table that we're going to fill in here. Notice the acceleration is constant, always 10 meters per second throughout his fall. But we want to know how fast he'll be going or what his velocity will be as he falls. Now, this is pretty straightforward because acceleration of 10 meters per second means that every second we're going to fall another 10 meters per second faster. Okay, so at the end of 1 second, he would be going 10 meters per second. At the end of 2, 20. At the end of 3, 30, and so on, right? So it's pretty easy to see how we get this. We're simply multiplying, right, the time that we're falling times the acceleration, and that gives us our velocity. So this leads us to our first question, or first equation for instantaneous velocity. It's simply equal to the acceleration times the elapsed time. Now, this is an important equation, so you want to make sure you get this in your notebook here. But this is the key right here. Velocity equals acceleration times time. Now, sometimes you'll see A, which we know is acceleration, but sometimes the small letter G is used, and this is just the acceleration due to gravity, right? So on Earth, when we use the value G, we're talking about 10 meters per second squared. Okay, that acceleration has that unique value. But not all problems will be free fall. We can have other values of acceleration besides 10 meters per second squared. All right. The next question we want to answer is, how far has the bungee jumper fallen? Okay, so to do this, we're going to take kind of a real basic math approach to it, using what we know about average velocity and displacement, okay? So what we want to do is analyze what was the average velocity during that first second of free fall. Because if we know the average velocity, then we can calculate the distance or displacement that he will fall. So we know he started at 10 meters per second. I'm sorry, 0 meters per second and ended at 10 meters per second. So if those were his start and ending velocities over the first second, the average would be 5. Now, how do we get the average? We simply add the start and the end speeds and divide by 2. So if we're averaging 5 meters per second for 1 second, that means we are going to fall a distance of 5 meters. Okay, so that's the first value we can put in here. We'll add 5 meters into our table. So after 1 second, we've fallen 5 meters. Let's do the same thing now for the time period between 1 and 2 seconds. So the second of free fall. So now we're starting at 10, right? And we're going to end at 20. Where are these numbers coming from? Right here, right? We're going to start at 10 and we're going to end at 20. So the average then would be 15. Again, we just add the two together and divide by 2. So that means we're going to fall an additional 15 meters. Now, that 15 meters is going to be this distance right here, right? This is going to be 15. So to get the total distance, we want to add the 15 to the 5 we have already fallen. So that means we will have fallen a total of 20 meters at this point. Okay, so let's continue this pattern here and see if we can figure out the distances for the rest of the time frames. So if we do this for the 3rd second, right, we will have an average speed of 25. That means we're going to fall an additional 25 meters. So 20 plus 25 gives us 45. And I'll let you do the math for the rest of this, but we'll go ahead and fill in these other values we would see at the end of 4 seconds. We've fallen a total of 80 feet. And at the end of 5 seconds, a total of 125. So notice as time goes by, we are covering a greater and greater distance because we are accelerating and traveling at a greater and greater velocity. Now, we don't need to go through this process every time to calculate our distance falling. There is an equation that tells us how far we fall. So x is our distance or displacement, and we can calculate it by taking 1/2 times the acceleration times the time squared. And so for free fall, we're going to put in the value of acceleration due to gravity, g, which is 10 meters per second squared. Okay, so we don't need to go through this process. We just did this to kind of understand where these numbers come from. But this equation allows us to calculate that. Now, oops. So let's just test it out once here and see if it agrees or just prove to ourselves that this equation works. So let's say we want to do this for 4 seconds of free fall. Okay, so x would be equal to 1/2, and we're going to put in 10 for our acceleration, and the time of free fall is 4 seconds. So don't forget to square the 4 seconds. So let's go ahead and simplify this. 1/2 of 10 is 5. And then 4 squared is 16. So if we multiply 4 times 16, we get 80 meters. Okay, so that answer, right, agrees with what we have down here for 4 seconds. Okay, so just to kind of prove ourselves, this equation works. It's a much simpler way, right, to figure out our distance than how we did it initially. All right, let's move on. This page here is a summary, and I will post this as a separate document under our class documents, because this will be a useful document to use for problems and tests ahead of us here. But it really has all of the equations that we'll be using to solve motion problems for a linear motion in a straight line. So the first is our speed equation, where velocity equals change in displacement over time. And notice we can solve this for any one of the variables. We could solve for distance or displacement. We can solve for time. Okay, so this is one of the first things we developed, right, when we started talking about speed and velocity. Here's the equation for acceleration that we just reviewed, right? We've seen that already. But here are the two new equations, one for velocity and one for distance, assuming that we are accelerating, okay? Now, if we're not accelerating, then we use one of the forms of this equation up above. But if we have acceleration, the velocity is not constant, that's the key here, then we need to use these equations to either calculate the acceleration, the velocity, or the displacement, okay? So we will get more practice over the next couple classes here of applying and using these equations to different motion problems. All right. The last thing we want to do is kind of look at an example, a little more complex example of free fall motion. What if we take a cannon, right, and shoot it straight up into the sky and then have it fall straight back down again? So here's the questions we want to ask. How fast is it going at any point along that path? How high will it go? And what will be the total time? Okay, so we're going to kind of work through this, applying what we've just learned about free fall motion, and use some of the equations that I just gave you. All right, so let's make some assumptions here. At time equals 0, when the cannonball just exits the cannon, let's say we have an initial velocity of 30 meters per second. Now, notice I have a positive 30 meters per second. Why positive? Well, the positive here means that the velocity's direction is upwards, right? Because obviously that's what we're doing. We're firing the cannon upward. We have a positive upward velocity. So that's why we're going to put, right, this positive and negative notes over here on the side to remind us that up is positive and down is negative. All right, let's go the next step here and see if we can fill in this table for what will our velocity be and our displacement at each second along our path. So let's go 1 second later. Now remember, acceleration is going to be in the downward direction, pulling down to the center of the earth. So note that's why we give it a negative quantity. So after 1 second, we are going to slow down by 10 meters per second. So if we were originally at 30, after 1 second, we're going to slow down to 20 meters per second. Okay, let's do the same thing 2 seconds later, right? We're going to slow down another 10 meters per second. So we're down to 10 meters per second as our velocity. And then at 3 seconds, let's say we reach our maximum height. So if we were at 10 at 2 and we slow down by 10, then we are actually going to have 0 velocity at the top here. So for that instant in time where we're neither traveling up or down, the velocity will be 0. Okay, now let's do our trip back down, right? Now that we're falling in the same direction as acceleration, our velocity will increase. So we're going to go from 0 to 10, but now it's negative 10 because we're falling back towards the ground. And then at 5 seconds, we would be at negative 20. And then at 6 seconds, we would be at negative 30 meters per second. Okay, so just subtracting 10 when we're on our way up, adding 10 meters per second when we're on our way down, all due to the acceleration due to gravity. Now, how about displacement? Well, we can do this by calculating the average velocity between times and then how far we would travel during that time. So we start at 30, we end at 20, that would give us 25 meters per second. So in 1 second, we would travel upwards 25 meters. Do the same thing for the next time interval. Start at 20, we end at 10, an average of 15. So 15 plus 25 would give us 40. These numbers maybe start to look a little familiar here. At the top, right, we're going to have start at 10, end at 0. So our average is 5 meters per second. So we will go to a maximum height of 45 meters. And then when we come back down, we're going to have those same heights on the return trip. So at 4 seconds, we're down to 40. At 5 seconds, we're down to 25. And at 6 seconds, when we hit the ground again, or back to where we started, we would have a displacement of 0. Okay, so a little more complex example of free fall motion, where we can apply our known acceleration of 10 meters per second squared and also calculate our height here. Now, what do we notice about the initial and final velocities? Notice that the initial velocity is 30, positive 30, and the final velocity when it hits ground is the same magnitude, but different direction, right? Because this is downward and the initial velocity was upward. Okay, so what we notice about it is that they are the same magnitude, but opposite direction. So whatever speed we have when we first are throwing the cannonball up is the same speed at which it's going to hit the ground, or vice versa. If we know the speed that it hits the ground at, that's also going to be the same initial speed or velocity that we launch it upward at. How about the time going up and down? Well, we noticed that it took us 3 seconds to go up and 3 seconds to come back down. So there's a certain symmetry around vertical motion here when we fire something straight up into the air and then have it return to its same starting point. All right, so that's it for today's lesson. Let me clear this. We've know how to describe the motion of an object in free fall. It falls at an accelerated rate of 10 meters per second squared. And we have 2 equations that we can use to calculate the speed and distance, or velocity and displacement, at any given point in time if the object is accelerating. All right, so that's it for today. The assignment that goes along with this is a Google form. You'll find that in Google Classroom.